Welcome back. This is tutorial 4a, question 3a. We'll use MATLAB to perform Laplace and inverse Laplace transform. As a note, please remember that MATLAB can only deal with unilateral Laplace transform. So even though the function is given as such, when we use MATLAB to solve it, MATLAB is solving it actually from this representation. It is only going to take the unit step multiplied by the function. That means it is only taking the causal part, and therefore it is only dealing with the unilateral Laplace transform. To use MATLAB, first start MATLAB and declare that t and s are symbols, are symbolic, and then we declare the function f to be e minus t, and then we are going to take the Laplace of f, which means e minus t, and the answer is 1 over 1 plus s, as expected. How do we compute the inverse Laplace? So if we are given f of s to be this, to compute the inverse Laplace, we simply tell MATLAB what is capital F, the Laplace, and then we use I Laplace to get the inverse of Laplace, and the answer is e minus t, as expected. So now you understand that it is very easy to use MATLAB to perform forward and inverse Laplace. All you need to remember is to declare the symbols t and s before we use them in the command Laplace and inverse Laplace. When you use MATLAB, you might not have the symbolic library. You must install that before you use SYMS. Let us now see the Laplace transform of various time signal. I'll just introduce some of the special signal that has special names. D of t is the delta function, and in the MATLAB it is called direct, DIRACT. And unit step has also a special name. It is called Heaviside. So we've declared u of t, or u, to be the Heaviside function, Heaviside t, and when we perform Laplace of u, we'll get 1 over s. You do not need to do comma s. You can try it, but it will be the same answer. Now we perform Laplace transform of e minus at times u of t. Even if you do not put u of t, the answer will be the same, showing that MATLAB only deals with causal signal, or the unilateral Laplace transform. So this is the time domain signal that you can type in using these commands, and this will be the results on the right hand side. You can compare the results on the right hand side with the table on this column. They are the same. These are more such command. This column is the time domain representation. This is the lookup table of the time domain representation for the Laplace. This is the command used to perform the Laplace as well as the inverse Laplace, and this is the results generated by MATLAB. MATLAB also can work with, or we can use MATLAB to verify time shift and frequency shift property. What is the time shift property? Is this when we have the signal x of t, ut, and this whole signal is delayed by t0. So not only xt is delayed by t0, ut is also delayed by t0. So the whole signal is delayed by t0. There is a close relationship between x of s and its delayed version. The answer is that we still have x of s, and the delay introduces this additional term e minus s, and then the delay is represented by that t0 over here. So this t0 in time becomes e minus st0 in the s domain. Now this example shows why or how we can use MATLAB to show that they are the same. So let's try. So first is we declare t and s to be symbols, t0 to be 2 seconds, and we have cosine t minus 2 u t minus 2 here, and we perform the Laplace transform of this, and we get the expression here, which is e minus 2s multiplied by what we expect would be s over s squared plus 1. This guy would be x of s, which is the Laplace transform of cosine t. And is it true? Well, we insert cosine t, we perform the Laplace transform, and we'll see that indeed this expression here that I highlighted is indeed the Laplace transform of cosine t. What we want to show is that we are going to multiply x by e minus st. So in fact, this is what we have done is e minus 2s multiplied by this guy. So this guy definitely is x of s. Alright, you can also try the complex shifting. In the complex shifting, the property is this: when the signal is multiplied by e s naught t, then all the s inside x of s originally will be subtracted by s naught. So what happened? Well, let's try the expression x equals to t cubed, and we are going to multiply x of t, so t cubed multiplied by e to t, and the answer is, this is the answer. And we also can try, this is t cubed, and we are going to substitute all s with s minus 2. So actually it is 6 over s to the 4. All the s is substituted with s minus 2, becomes 6 over s minus 4 to the power 4. So this function substitute all s by s minus 2, showing that these two answers are the same. So we are just using MATLAB to verify these two properties. That's all. Thank you.